Welcome to this explainer. Right now, modern computing is barreling toward a fundamental physical limit. But today, we're unpacking a mind-bending shift that's poised to solve it. For decades, our digital lives have run on the exact same principles, but we are absolutely hitting a wall.
So let's just get right into it. Think about the last 60 years. The entire digital world has been built on one simple idea. Move electrons around fast enough, and boom, you get computing. Charge is on, that's a 1. Charge is off, 0. It happens billions of times a second. It's elegant, it works, but right now, it is rapidly running out of road. Which leads us to a pretty radical question. What if we just stopped moving electrons altogether?
To understand why we'd even consider that, look at this massive number. Right now, data centers are eating up roughly 1 to 2% of the entire world's electricity. And with the explosion of AI workloads, that number is climbing fast every single year. The real crisis here isn't just that it's hard to make transistors smaller anymore, it's an energy crisis. You see, as silicon transistors shrink down to the nanometer scale, they get leaky. They start bleeding immense amounts of power, even when they're totally turned off. It's a microscopic leak, sure, but multiply that by billions of transistors across billions of devices, and it's a total architectural nightmare.
Section 1. Spintronics, the magnetic solution. Honestly, the very physics of silicon is becoming the enemy of the industry it built. We literally can't afford the electricity bills to keep pushing silicon the way we always have. So, we're forced to look at an entirely different paradigm.
Enter spintronics. Now, you probably know electrons as tiny particles with an electrical charge, but they also have a quantum property called spin. They can point up or they can point down. Traditional silicon computing completely ignores this, but spintronics, it makes this ignored property the whole point. Instead of checking whether an electrical charge is flowing through a gate, spintronics represents data using magnetic orientation. We are basically flipping tiny magnets instead of moving an electric current. Magnetic moment points one way, that's a 0, points the other, that's a 1.
And this illustrates the core advantage perfectly. Silicon relies on moving charge, right? Which makes it incredibly volatile. The absolute second you cut the power, silicon forgets everything. It's gone. But a magnetic device holds its physical orientation indefinitely. It requires exactly 0 standby power to maintain its state. And that non-volatile nature, that is a literal game changer for energy consumption.
Moving on to Section 2, the 3-in-1 transistor. Now, using magnets for storage isn't pure science fiction. We already have things like MRAM for memory today. But what's coming next is applying those exact same principles to actual computation.
And that brings us to a massive breakthrough from September 2025. MIT engineers successfully built a working magnetic transistor. They essentially swapped out silicon for a highly unique 2D material called chromium sulfur bromide. It's antiferromagnetic, meaning its internal magnetic fields cancel each other out, so it stays highly stable. But here is the real kicker. It is air-stable. That is the difference between a neat little trick in a lab and something a massive factory can actually manufacture. In this material, the magnetism and the electronics aren't two separate things. They act as the exact same system.
MIT Associate Professor Lucia Liu hit the nail on the head here. Because you can switch cleanly between magnetic states using just an electric field, this transistor completely cuts out that massive energy overhead of constantly shuttling data back and forth between separate memory banks and logic processors.
So what you get is a true 3-in-1 action. You've got switching, amplification, and built-in memory all happening in the exact same physical space. This fundamentally changes what a transistor even means at an architectural level. It is a completely new operating principle, baked right into the device itself.
Section 3. Industry momentum. And let me be clear, this is absolutely not just some academic curiosity. The world's biggest foundries, the giants who actually physically make our chips, are already heavily invested in this transition.
Just take a look at the foundry space. Samsung has already developed an 8-nanometer process and is pushing hard for 5-nanometer production by 2027. TSMC is targeting embedded MRAM specifically for automotive and edge AI applications. Over at Intel, they're working with Georgia Tech to design 7-nanometer devices aimed directly at those power-hungry data center workloads we talked about. And Everspin, they are literally shipping a 1 gigabyte commercial product right now alongside IBM.
And backing up that aggressive push on the hardware side, the spintronic memory fabrication market is projected to grow at an incredible 18% compound annual growth rate through 2030. That kind of financial momentum, it just doesn't show up for technologies that only exist on paper. The industry clearly knows what's coming.
Section 4. The future of hardware. Now, let's be precise and temper the hype just a bit here. Silicon is not going to vanish in the next 5 years. Your high-performance CPU running at 5 GHz, that's going to stay silicon for the foreseeable future, because magnets do switch a little slower than the absolute fastest high-voltage silicon.
What's actually happening is more of a quiet bifurcation of computing hardware. They're going to coexist. Silicon keeps the high-speed, high-power central computing tasks. Meanwhile, magnets take over the areas where computing is actually seeing its biggest physical growth. Low-power, always-on, edge AI, Internet of Things sensors that need to run on a tiny coin battery for years, and aerospace or defense hardware. In extreme radiation environments, magnetic states are incredibly resilient compared to charge-based storage. Zero standby leakage and instant-on capabilities, that becomes an absolute superpower out there.
But we have to be real here. Obstacles remain. This isn't magic. There is a fundamental materials engineering challenge at play. It's a constant tension between stability and switchability. You need the magnetic bit to hold its state reliably without accidentally flipping, but you also need to flip it intentionally using very low energy, at the nanometer scale. Plus, introducing brand new magnetic materials and deposition techniques into multi-billion-dollar existing fab plants adds cost and complexity, even if it doesn't require a total ground-up rebuild.
So, the most crucial point is how this directly impacts the hottest topic in tech today, AI. Moving data from memory over to a processor is modern computing's single highest energy cost. But a 2025 paper in Nature Electronics showcased a fully parallel spintronic compute in-memory chip. What it does is perform lossless matrix operations, which is the complex math AI relies on, directly inside the memory itself. When thermal limits and electric bills are your true bottlenecks, an architecture that calculates directly in magnetic memory lets you run massive AI models right at the edge. It does vastly more with a fraction of the energy.
Ultimately, this leaves us at a fascinating crossroads. Power, not transistor count, is now the primary constraint in global computing. If the entire AI build-out is running face-first into a wall of power consumption, and the absolute best answer comes from flipping magnetic moments instead of pushing electrons around, we have to ask how long until this completely reshapes the hardware in your pocket. Think about it. Thanks for joining me on this explainer, and keep your eyes on the magnets.